Welcome. I'm here to share with you some interesting insights about the manufacturing data from this beverage manufacturing company. Uh, I'm coming to you as a data science, and so what I can tell you about the information inside this data set is relationships. And I have done a little bit of background research to try to guess at some interesting and important information about the business. Um, but what I can be confident to share with you is the relationships. And hopefully the information that I present to you in this short presentation will be useful to you in improving your bottom line in manufacturing output and product quality. So I'm now, if you want to follow along, I'm now using the PowerPoint presentation, and I'm going to walk through the slides one by one. So at various times I'll mention which slide I'm on so that you can follow along. So we'll start out with an introduction, and I'm going to define the business context that I suppose we're dealing with, and that this is a beverage manufacturing company for alcoholic beverages with a carbonation process in it. Well, I'm also going to introduce the important objectives, and then we're going to get into some of the interesting process changes and some of the interesting things that you can learn from the data set about the differences in products, the brands, A, B, C, and D. And then finally we'll get into some unusual process changes, which may require some further follow-up. So first of all, description of the business. So based on the data set, it appears the business is selling carbonated beverage that also contains some alcohol content. And there is multiple product brands. This manufacturing process occurs from Saturday. Their work week is from Saturday until Thursday, and Fridays off, or at least they're not collecting data on Fridays. And all of the products are all on the same continuous product line. So switches, they're not parallel trains. There's one line that has all the products on it, which makes some switches occasionally. Some important objectives is, first of all, to have a fast manufacturing rate. This is really important for a beverage manufacturer. This is how they compete with one another. And minimal downtime operations. Additionally, what's also important is product quality, to maintain consistent products, low oxygen content, low oxygen contamination, and the product consistency, in particular the sugar content and the alcoholic content. So first, let's start with the manufacturing rate. So there's a parameter in the data set labeled as MNF flow, which maybe that's the manufacturing rate. So this MNF flow is related to mostly three variables in the data set: hydrogen pressure 1, hydrogen pressure 3, and the filling speed. And generally is increasing with all three of these. So the key point is that and normally in the data set there's fluctuations and variations in the manufacturing flow that are corresponding to changes in the hydrogen pressure 1. There was also some major changes that were occurring using this filling speed parameter. The filling speed parameter the changes appeared to be done through some testing and by human intervention. And the overall result is that these changes overall resulted in about a 28% increase in the manufacturing flow when you control for the effects, the main effect of the H pressure 1. So the net conclusion is, as a result of all those trials, a higher filling speed results in higher manufacturing speed, suggesting that maybe the filling speed is a bottleneck step. Now, something that else that is interesting about this finding is that there does not appear to be any adverse effects on any of the other operating parameters or quality parameters, suggesting that this was an overall improvement. So, good job. The next area of analysis is on some changes that were observed in the oxygen filler. Now, if this oxygen filler is a representation of the oxygen amount in the beverage, then we'd want to keep that low, because oxygen contamination in beverages, carbonated beverages, can lead to the risk of a premature fogging, which is essentially release of bubbles and contamination, and you lose the carbonation effect. So ideally you want to keep it low. Now at the same time, any manufacturing process has variations. So in this particular process is no exception, and there are some spikes. And so a good recommended value is 0.05 grams per milliliter, but when you realize that there are some spikes, it may mean that you need to actually operate even lower than that to make sure that even the spikes don't go above. And so there were some changes also that appeared to be testing, non-random changes, and the overall result is that changes in the bowl set point, and so by the name set point, probably it's something you can control, these changes overall resulted in a reduction in the oxygen filler parameter. The oxygen filler parameter, however, did not really show too much further benefit after about a set point of 120. So changes from 80 to 120 show about a 50% reduction from values around 0.035 to 0.017, but there isn't a substantial observed further improvement from 120 to 140. So 120 seems like a good place to keep it. There did not appear to be any detrimental impact of these changes in the bowl set point to the manufacturing flow. So again, it appears as though this is a good move and an overall improvement. So, well done. And so now we've talked about the two improvement areas in product quality with the oxygen filler, and also the improvements in manufacturing speed. So now I'd like to share a little bit about what we can tell about the differences between these products. Now the main difference between the products is their alcohol content, or the balling parameter, which is labeled in the data set. So there's a formula in the beer manufacturing to convert between sugar and alcohol content, and it's known as the balling formula. And so that's why maybe, and the range of values is pretty close to the alcoholic content of popular beers. So maybe this is the alcohol content parameter. So I will be referring to it as alcohol content, or ABW, under these presumptions. So the main difference between these products is their alcohol content. And products A and D have about a normal alcohol content, a little bit low, but similar to your very popular brands like Carlsberg, Budweiser, around 3.5%. Products B and C have very low values, and in fact may be considered as non-alcoholic. So this is a kind of new product trend. So B and C may be new product lines. So the alcohol content, the alcohol relative, which is a higher value, and the carbonation relative parameters, they're all very highly correlated. So there's only really one major feature of these products that distinguishes them from one another. There is actually 2 degrees of freedom here, which I'll get to in the other slide. But for the most part, there's one parameter that's more or less characterizing the big differences between these products. Now the difference between these products is much more apparent for A and D and B and C together than within B and C. So B and C look very, very similar to one another and can only be slightly distinguished statistically. And in fact, they may actually be more or less practically the same products from a statistical point of view. Another thing to highlight before we go on to some more details about this relationship between these qualities is that there does not appear to be a relationship between the product quality parameters of the alcohol content, density or sugar content, and the carbonation amount and the operating parameters that are in the data set. Of course, the way you ferment and so forth would have an effect, but it doesn't appear that the fermentation process is in this data set. So for this data set, operation and quality appear to be independent of one another. So a little bit more about the characterization of these products. It's a little bit more accurate to say that there's two parameters that fully characterize these product differences. And when you present this on the chart of the alcohol relative and the AB and the Balling parameter, you can see that their relationship is a curve, which means that these two parameters in that curve, the kind of the slope and the intercept, fully characterize the differences between products. And so you can see that this slope and intercept are different for A and D, but are kind of similar for B and C. And if you were to use some standard machine learning techniques and support vector machines, it would in fact be able to identify a difference and discriminate between B and C, but generally speaking, they're quite similar. So now that we have covered main overview of the data set in terms of the product quality, manufacturing, and the differences between brands, I'll go a little bit more into anomalies and unusual process changes that you may want to be aware of. So the first one I'm going to get into is the calculation of the sugar density from the alcohol content. So there are many beer manufacturers do not, they use density as a way of calculating and monitoring the alcohol content because that's a more expedient way of doing things. So there's calculations involved. So it appears as though that's what's being done in this process data set. And so we have two parameters, the density parameter and the Balling parameter. And density may be sugar content of the wort or of the final product. I don't know, but it's probably the wort, and the Balling parameter or the alcohol content. So there is a formula out there on the relationship between these two, and the only additional parameter that's missing in this formula is the final alcohol content or the real extract. So there was a change that had occurred on 1st of February which shifted this relationship in the calculation. Now, I don't know if that was done intentionally or if it was a software change, but most likely this was not a process change by the appearance of the characteristics of the shift. So if this was intentional, then you may already know about it, but if this was unintentional, then I would recommend that you have a look. Next, another anomalous event was the characteristic changes in the relationship between the carb flow and the fill pressure. So I don't know what these parameters are, but the key message here is that on 4th of January there was a lowering of the carb flow from around 3,000 to pretty consistently at 1,050. Before the change, there was a considerable amount of variation in this parameter of the carb flow between around 3,000 to 4,000. This variation was substantially reduced after the change. And a way of explaining why the variation was reduced is that there was a link previously, a relationship between the carb flow and the fill pressure. And the variation in the fill pressure disturbance noise continued before and after the change. It was unchanged. But what changed was the relationship between the two. So this overall without knowing too much more about the situation, appears to be an improvement because you've reduced process variations from one of your parameter, and that's usually a good thing. So you may want to investigate more to learn about, this particular change, and if there's anything further you can do for more improvements. But overall, this is probably a good thing because you've reduced the variations. All right. Finally, as a minor point, the air pressure variable had an unusual blip up that had occurred, and then it went back to a normal value. And the blip up was way above the noise range of it's more than 144. The results of this change did not affect really any of the parameters, except to a minor extent it affected the pressures and consequently the manufacturing flow. So in order to keep the line running at optimal speeds, it would be recommended not to do that again unless there's some other information about this change. So that's all I had to share about this data set. There's a lot of information in the data set. There are many further areas to explore. There's some aspects of time series dynamics and some process noise fluctuations that could be further analyzed using many different data analysis toolkits. But for now, these are the main insights that popped out of the data set that I wanted to share with you. So thank you for your time.